Hello, this is Dr. Muhammad from AIBM Secure Community, and in today's lecture I'm gonna talk about AES S-Box, types of S-Box, and Galo inversions, as well as I'm going to talk about affine transformations. The title of today's lesson is AES S-Box, types of S-Box, GF inversions, and affine transformations operations. Today's agenda is S-Box introductions, S-Box operations, GF inversions, affine mapping transformations, full examples, and references. As a simple introduction about S-Box, in cryptography, the S-Box is a basic component of symmetric key algorithms which performs substitutions. The S-Boxes are typically used to obscure the relationship between the key and the ciphertext, thus ensuring Shannon properties of confusion. The Shannon properties consist of two properties. The first property is confusion, and the second property is the diffusion. The S-Box is related to the confusion property, and P-Box is related to diffusion property. There are different types of ciphers use S-Box, like Advanced Encryption Standard, AES, Data Encryption Standard, DES, Bluefish, and there is so many other ciphers use S-Box as well. In literature review, there is so many methods used to construct the S-Box, like algebraic methods, which contains three types: Galois fields, Galois ring, projective general linear group. The second one, chaos-based methods, which consists four types: continuous chaotic system, differential equations, discrete chaotic system, and interval maps. Third one, chaotic assist optimization method, which consists four types: ABC optimizations, traveling Salesman optimization, Gary-Wolf optimizations, and anti-optimizations. And last, some special methods like Quest group Latinus sequence LA semi-group. To construct S-Box in algebraic method, you have to consider two steps mathematical transformations. The first one, Galo field inversions, and the second one, affine mapping. In the first part, each input A, the inverse is computed. The inverse can be directly substituted using the multiplicative inverse. So, this transformation is known as Galo field inversions. Second, the affine mapping operation takes the output result of Galo field inversions. GF inversions. The GF inversions is the first operations in AES S-Box. The GF in the inversions is used with Galo field 2 to power 8. Inversion in GF 2 to power 8 is the core operation of the by substitution transformation in AES SBox. For a given final field, GF2 to power m and the corresponding irreducible redirection polynomial px, the inversion is defined as A inverse x dot ax equal 1 mod px, px which is AES polynomial. The below table shows the values which are used within the SBox of AES. The table contains all the inverses in GF2 to power 8 within px. Here, px equal x8 plus x4 plus x3 plus x1 plus 1 in hexadecimal. The GF inversions, it is the first operations in AES. The GF inversions is represented within Galois field 2 to power 8. All the values are represented by using Galois field 2 to power 8. All the values in hexadecimal value. To get the value of any input to SBox, the cross of row and column is used. So the value of 3D SBox is equal to 27 in hexadecimal within Galois field 2 to power 8, where 3 is the row in AES table and D is the column in AES table. So the cross between 3 and D is equal to 27 in this table. GF inversions example. Now we know how to get the value in the AES table. According to the previous example, the cross between the row and column and the result was 27 in hexadecimal. But the main question is 27, where did it come from? So the example here, how to get the inversions of 3D value, which is 27 in hexadecimal within Galois field 2 to power 8. First, we have to take the value in hexadecimal and convert it to binary. So when we convert 3D to binary, the result will be 00111101. Then we convert the value of 3D to a polynomial, and the result will be x5, x4, x3, x2 plus 1. Now we have another question. How to convert 3D to polynomial? First, we will take the value of binary 00111100. This value of 3D in hexadecimal, and then convert it to binary. Second, we will write the polynomial for 8 bits as below. x7 plus x6 plus x5 plus x4 plus x3 plus x2 plus x1 plus 1. Then we will delete each polynomial has the 0 value of binary. x7 has 0 value in binary. x6 has 0 value of binary and x1 has 0 value in binary. This one and this one and this one. So x7 equals 0 in binary, x6 also equals 0 and x1 also equals 0. The result will be x5 plus x4 plus x3 plus x1 plus 1, and this is the polynomial of 3D hexadecimal value. And then we will put the AES polynomial px equal x8 plus x4 plus x3 plus x plus 1. Now we will divide the AES polynomial within 3D polynomial. First, we will multiply the 3D polynomial within x3. The result will be x8 plus x7 plus x6 plus x5 plus x3. And then we have to delete x8 with x8, x3 with x3, and the result will be x7 plus x6 plus x5 plus x4 plus x plus 1. Then we will multiply by x2, and the result will be x7 plus x6 plus x5 plus x4 plus x2. Then we will delete x7 with x7, x6 with x6, x5 with x5, x4 with x4, and the result will be x2 plus x plus 1. The B operations will be dividing the 3D polynomial with the result of A operations. The first we will multiply the result of A operation by 3. The result will be x5 plus x4 plus x3. Then we will delete x5 with x5, x4 with x4, x3 with x3, and the result will be x2 plus x1. Then we will multiply by 1, and the result will be x2 plus x plus 1. Then we will delete the x2 with x2 and 1 with 1, and the final result will be x. In C operations, we will divide the A result on B result, and the final result will be 1. When we get 1, that means it's correct. We can continue. Now, after getting the result of A operation and B operation as well as C operations, we will do some basic mathematical operation in order to get the inverse of 3D. Here we have the result of A operation, B operation, C operations. Here we have the main equations and the divide on and the remainder. Main equations, divide on and remainder. Also we have the main equations, divide on and the remainder. We will do the operation one by one. First we will go to C operations, then we will transfer these
equations to this side, and the result will be like this: x2 plus x plus 1 minus x plus 1 multiplied by x equal 1. And because of we don't have in the binary minus, so we will convert this minus to plus, because in binary we have only 0 and 1, we don't have minus. So the result will be like this: x2 plus x plus 1 plus x plus 1 multiplied with x. Then we will start with first two equations, equation C and equation B. We will multiply these equations first with the main equations of B and then with the remainder. So after multiply the C equations with B equations, the result will be like this: x2 plus x plus 1 plus x plus 1 multiply with x5 plus x4 plus x3 plus x2 plus 1 plus x plus 1 multiply with x3 plus 1 multiply with x2 plus 1 plus 1 equal 1. To do simple operation of these mathematical, we will do like this: x plus 1, x5 plus x4 plus x3 plus x2 plus 1 plus square bracket 1 from this side plus x plus 1 multiply with x3 plus 1, close the square bracket, x2 plus x plus 1 equal 1. Then we will do simple mathematical operation as well as for this one: x plus 1 multiply with x5 plus x4 plus x3 plus x2 plus 1 plus 1 plus x4 plus x plus x3 plus 1 multiply with x2 plus x plus 1 equal 1. Then we will use these equations with equation A. We will multiply all these equations with this side first time, and then we will multiply with this side also. Now A equations. So the result after multiply these operations with this side of A operation and this side of A operation, the result will be x plus 1 multiply with x5 plus x4 plus x3 plus x2 plus 1 plus x4 plus x3 plus x multiply with x8 plus x4 plus x3 plus x plus 1 plus x4 plus x3 plus x multiply with x3 plus x2 multiply with x5 plus x4 plus x3 plus x2 plus 1 equal 1. It's big operations and it's big equations, so let's do some reducing for these equations. x4 plus x3 plus x multiply with x8 plus x4 plus x3 plus x plus 1 plus, we will take this side and this side, plus square bracket x plus 1 plus x4 plus x3 plus x multiply with x3 plus x2 and close the square bracket, multiply with x5 plus x4 plus x3 plus x2 plus 1 equal 1. Then do simple reducing for these equations, and the result will be x4 plus x3 plus x multiply with x8 plus x4 plus x3 plus x plus 1 plus x plus 1 plus x7 plus x6 plus x6 plus x5 plus x4 plus x3 multiply with x5 plus x4 plus x3 plus x2 plus 1 equal 1. So this is the big equations. In order to reduce these equations, we will do some mathematical operation on these equations. Then the result will be x4 plus x3 plus x multiply with x8 plus x4 plus x3 plus x plus 1 plus x7 plus x5 plus x4 plus x3 plus x plus 1 multiply with x5 plus x4 plus x3 plus x2 plus 1 equal 1. So the result of this side will be 0, because if we multiply this side with this side, the result will be more than x8, and if the result will be more than x8, that means this side will be 0. So this is 0, and this side will be same, x7 plus x5 plus x4 plus x3 plus x plus 1 multiply with x5 plus x4 plus x3 plus x2 plus 1 equal 1. So if we calculate this polynomial with the binary value and calculate this polynomial with the binary value, the result will be 1 0 1 1 1 0 1 1, and this is PP, and this side will be 0 0 1 1 1 1 0 1, and this is 3D. So now we have the inversion value of 3D, which is PP. This PP, we will use it with the next operations, affine mapping.
Affine mapping or affine transformation. The AES S-box is constructed using the affine transformations as the second operation after the S-box inversion. The affine transformation equations is y equal ax xor c mod mx, where A is a 8-8 matrix with an entire Galois field 2. C is a column matrix in Galois field 2. Mx is any irreducible polynomial in Galois field 2 to power 8. This is the binary matrix 8 by 8 in Galois field 2. And PP is the result of the previous operations, Galois field inversions. And this is the column matrix in Galois field 2. The result is 27 in hexadecimal, which is the gross of SBox 3D in AES table. We have important notes here. The multiplications, equal, and operations. Here, when we do the multiplications between the 8 by 8 matrix with the PP, we have to do AND operations. And the result of these, we will do addition. That's mean XOR operations. Finally, we have the reference. We have three important references. The first reference from Wikipedia, which is talk about Rajendal SBox. And the last two reference, it's from Clarivate journals, which is important journals. Thank you for watching, and see you again in the next lesson.